0.4 amperes times, since this is the voltage of the power supply, this is the equivalent resistance.
Okay.
So this is for the overall power supply, this is the overall resistance, times 7.916 would be, and you get,
4 volts even.
pardon?
4 volts even.
No, not buying that. 2 times 7
Oh,
is
sorry,
14.
19 volts even. My
Okay,
bad.
19 volts.
Yeah.
I was kind of confused.
19
Is this
volts
light bulb
even.
gonna be running for more than 8 hours a day? Because if it is, then we gotta do the 70% opacity rule on it and times that by 0.7.
I was keeping it simple, I just didn't want it to break during the lab itself, so
Okay,
that,
cool.
so I'd have to replace it. Because I have had those labs with just people over cranking the voltage.
Could you just really quickly go over the 2.916 ohms?
2.916 ohms is the equivalent resistance of this piece right here.
Okay, gotcha.
Oh, so that's 156.
So that's R2, right,
Right, any other questions before we tackle what I feel is a more interesting question?
I thought this one was pretty interesting.
Just wait till you see the next one.
This one made sense.
Jacob Black, that's here.
All right. Of course, I put the pin down somewhere, there we go. Now, originally I was using my finger on this instead of the stylus, but I know it's blistering, so that's why I'm going for this. All right, so the next question is, instead of the 2 ohm being a light bulb, the 5 ohm is a light bulb. That's the 2, here's my light bulb. 3, 5. 1, 6. If my maximum put current across here is, it's supposed to be max, is 2.4 amperes.
Isn't it the same?
It is not the same. Because whatever current's coming out of the power supply will split. This is 2.4, this is something, and the sum of those is what we'll be using to figure out the voltage here. So, let's figure out how much current has to go this way. If this is 2.4 volts, 2.4 amps, how much current is flowing around? First off, more than 2.4 amps or less than 2.4 amps?
Should be less, right?
Should be less, why?
Something tells me from the context clues of the problem that it was gonna blow.
Because the current's gonna travel the least resistance, and that's a resistance of 7 ohms on the right, and then the left is, the path is a resistance of 5 ohms.
Okay, yeah.
Okay.
So it's simple to treat this as there's my 2, there's my 5 bulb, 3, and 7.
Okay. And
I
that's,
know this is gonna be 2.4 amperes.
that circle's a light bulb, right? That,
Yes,
okay. So that's 2.
typically the circle around the resistor indicates light bulb. There are a couple ways of going about this. To me, the simplest one is voltage. I have a junction here. A junction here and a junction here. These are in parallel. Objects in parallel. What is the same for objects in parallel?
The voltage is the same?
Yes. Because whichever path I take, I have the same difference in potential.
Okay.
So my potential here, well, I'm using Ohm's law, I know that potential across that is just going to be current times resistance, which is 2.4 times 5.
10.8.
What is it?
10.8. Oh, wait, no.
No.
12?
Well,
Yeah, 12. Yeah, 12 volts. So if I have 12 volts going this way, I gotta have 12 volts going that way. Potential difference between any two spots, no matter which path you take, is the same. So that way or that way is the same, so therefore I can figure out the current flowing across here. It's delta V over R, again, Ohm's law. And so that is 12 divided by 7. 157, so 1 point. Something. 6.
1.7, 1.4.
1.714.
Yeah.
28.
Yeah.
3.
5.
5. So that repeats. All right, so I know the current now flowing down this path. I know the current flowing that path. So the current flowing into the junction, Cherepov's junction rule, has got to be the sum of those two. So 2.4 plus this. So the current flowing here is 4.114285.
Yeah.
That's a 1-1. So now I know the current that's going to be has to flow out of the power supply. Since the power supply is supplying the power for everything, we're down to here. Except now my current coming out of the power supply. So delta V power supply is equal to the current times the equivalent resistance. In essence, is what we did here. So 4.11, however you want to take it. 4 times equivalent resistance 7.
32.57 volts.
So we end up with, well, one, it's a higher resistance, but also because what's coming out of the power supply splits, we can get a much higher voltage than what we had before.
So, just out of curiosity, when is that a good thing and when is that a bad thing? Why would you want to change the voltage of your power supply?
Dimming lights,
Okay.
that's, you have your phaser set to stun versus kill.
That's valid.
It's good enough for me.
Understood.
Oh, so when you have dimming light switches, that's what they're adjusting? When you have the dimming light switches with the.
No, yeah.
That's what it's adjusting, okay.
They're adjusting what?
Huh.
If they're, I'm saying adjusting resistance, sorry, I was thinking adjusting resistance, they're adjusting potential. It's a potentiometer as opposed to a resistor. There's some subtle differences about, in a simple circuit, changing one changes the current flowing through the other, or I can, no matter which one you change.
Okay. Oh,
But-
So given like Ohm's law, it could be like any of three things it could be changing. It could like, increase the resistance of it, that would change the, volts times the capacity. Anyway, or you could have like a lower amount of voltage and the resistance and capacity would stay the same, or you could have a lower amount of capacity, right? Sorry, I'm
Except you can't do, I was trying to think, can you lower the current without adjusting one of the other two? But I think current results from
Sort of set it.
one of the other changes.
Yeah.
Unless you had a bucket of charge and you just had different buckets. I guess that's adjusting the voltage.
But aren't they all
this is good.
adjusting based off if you change the other two?
Well, I was trying to make the claim that the current, you can't adjust the current directly to
Oh.
affect either of the other two.
Okay.
That
You
the
have.
current is always going to be a result of
changing your other bucket.
Right. That's the thing, you're gonna change the taste of the egg by messing with the egg once it's cooked. Or like if you're trying to imagine.
I'm lost in the metaphor. Sorry.
Sorry,
Okay,
I'm trying to
like,
hear you.
You ever tried, when you're making food and you want it to be one way or another, you worry about it with your ingredients and what you're gonna put in it, rather
Right.
than look at the end product. I get that.
Yeah, yeah.
That's the-
I think that works. Right, and then the last part of this is they're all capacitors now with those values, but units of farads instead of ohms. What's the equivalent capacitance? And so you go through the same process you did the first time, except make sure you get the formulas right. So first thing, I've got the series, still adding series first, but it's 1/1 plus 1/6 is 1/. My equivalent capacitance for 1 and 6.
I got 0.857 farads.
Now for those, that's after you've done the reciprocal at the end. Because that would be 7/6. And take the reciprocal, this would be 6/7. If you're fraction fans, go for it. If you're decimal fans, which I personally think would be easier in the long run, go for it. So now I have that. Let's clear some space here. That was 1, 6, 5, 2, and 3. All right, so we add those two together, we get the, again, adding when you're doing the reciprocal bit, the final result is less than the smaller one. So we end up with something smaller than 1, which makes sense. So I've now got my 2, my 3, my 5, and my 0.857. They're all farads. Now what?
Add the parallel ones.
Yep. So I got 2. I've now got a 5.857. And a 3.
The inverses.
So 1/, my total equivalence is 1/2 plus 1/5.857 plus 1/3. The two biggest mistakes I see students make is flipping resistances, resistor sums and capacitor sums, and forgetting to take the reciprocal at the end. I guess the next big mistake would be, for instance, if you have done 5 and 6 in parallel, ignoring the 1, that's another common rookie mistake. So what do we end up with?
I got 0.996 farads.
Yeah. Okay.
Yeah, that's what I got as well.
I'm feeling good then.
I feel really dumb for asking this, but
Go for it.
yeah, why did you flip the 7/6 to 6/7 right here when you were adding the 1/1 plus 1/6?
1/1 plus 1/6 is 7/6.
Yeah, 7/6, yeah.
So that's equal to 1/, the equivalent. So therefore, the equivalent is you take the reciprocal. So the-
Oh, that's 1/7/6, is that what you're saying?
No. What I have here is,
Yeah, no, technically, yeah, it is 1/7/6.
I have 7/6 is equal to 1/, my equivalent capacitance. Therefore, my equivalent capacitance is the reciprocal of that.
Okay, so that makes sense, thank you.
Does that Apparently I misheard you, or.
No,
That makes
sorry, it was just dividing it down in the denominator there. Didn't realize it was in there.
Essentially, you cross multiply.
Yeah.
Wait, eventually you cross multiply?
No, like you're just switching the stuff.
Yeah.
Yeah. That goes over there. That one goes on there. So and then that 6 doesn't go up because it's being divided. So it's got.
Yeah, two fractions equal to each other, I can move anything across the diagonal.
Hey.
So,
Thank you.
Other questions?
I said cross multiply, but I didn't mean cross multiply.
I figure at this point, you know what you're talking about. All right. Yeah, for the first couple of years, I didn't think of this problem. I felt like this was such a nice problem, the next one. I give you the battery, I give you resistors of various sizes, give you some adjustable things, and you have a target current.
Pretty cool.
So for this particular one, 10-volt battery. And then I have, that's the voltage of my power supply. Then I've got resistors, resistance of 2 ohms, 5 ohms, 6 ohms. I got one variable resistor, which is anywhere from 0.5 ohms to 2.5 ohms. And then a kid's toy, so this is my variable resistor. And then my kid's toy, 1 ohm. That's my toy. And the current across the toy is 3.7, ooh, that's bad notation. Plus or minus 0.100, parentheses around that, or. It was 2017, they were wild and reckless days.
What does T stand for?
Toy.
Toy.
All right, design a circuit. Now the rules are, you have to use all the components. There must be a non-negligible amount of current flowing across each of them. And, yeah, so whatever you choose for the variable resistor, you need to state what you're using. There are several approaches to this. There's more than one correct answer. My recommendation is that you have whatever current's coming out of the power supply is the same current that's flowing across the toy. That, I think, simplifies it. Then you don't have to worry about the split current and going, well, how much actually is going across the toy?
Can you say that sentence one more time? Would you mind saying that sentence one more time, please? Just keep something the same.
My recommendation is whatever current is coming out of the power supply is the same current going across the toy. So let me just set up my power supply here, 10 volts. And if I want that to be the case, I'm gonna put the toy right in there. This is a 1 ohm resistor. And then the rest of them, I got room for playing. My next recommendation is, what does my equivalent resistance need to be in order for the current coming out of the power supply, and thus across here, to be 3.75 amperes. I shoot for perfect and, see how close I can get. So I know that my voltage of my power supply is equal to my current times my equivalent resistance. So my equivalent resistance is equal to 10 over 3.750.
2.6 repeating.
I know that 1 ohm of my equivalent resistance is taken up by my toy. So So whatever is here has to be 1.6 repeating ohms. Well, right off the bat, the only thing that I have less than 2 ohms is my variable resistor here. So something's going in parallel. Gotta have something parallel because I need to get, like, the total of those 4 resistors has to be 1.67 ohms.
Is it supposed to be 2.6?
The two bottom forms are getting in there.
Well, because you wrote 2.6 over there for the resistance, so why are you putting 1.6 over there?
Cause he's taking into account
Oh.
the employee's resistance
Oh,
up there.
okay.
Yeah, the total is 2.6 repeating.
So he's done with that side of the circuit, now he's gonna come up with a bunch of parallel. Well,
Or something's parallel, like how much is parallel. So I'm just gonna start out with, well, what's 1/2 plus 1/5 plus 1/6, and then the reciprocal of that. What does that get me?
sorry.
We have to add them before we do this reciprocal?
That gives you,
Yes.
the reciprocal of that gives you 1.15.
Oh, you're typing on a calculator. Pretty smart.
You get the same thing? Anybody get the same thing?
Three six.
I have mine in wrong.
One
Yeah, I got one.
Yeah, I think I can see what it is.
1.15.
Hector's about to come up with a fraction.
20, 30, then 6/30.
That's what I got.
26/30, sure. 26/30, which becomes 30/26, which is, yeah,
15/30.
that's about right.
I'm gonna get, I think this is somewhere around 1.15.
Something like that.
Now,
Yeah, it is.
so I'm below this, but is the difference in this range right here?
We're shy of it. We're 0.05 over, 0.05 ohms over.
So if I did the 1.15 and, all right, so now, again, I was targeting an exact value, but I got a little bit of wiggle room here, so let's see if I can get away with it. If I did